Hello, everyone. My name is Yasmeen,
I'm Letícia.
and today we're going to be talking to you all about our cleavable comonomer additive strategy to reprocess, reintroduce, and innovate in tough-to-degrade plastics. So I'm not going to belabor this point too much, as I'm sure we're all well aware, we need solutions for plastic waste urgently. And when we say this, we often think of all the plastics that we can recycle. We want to make a clear distinction. Thermoplastics are what we typically think of. This is the type of thing that goes into our water bottles or our food packaging. And you can think of them as kind of polymer chains, similar to spaghetti strands, that can move past one another, making them remoldable, meltable, and dissolvable when heated. The type of material that we're talking about today, though, are thermosetting plastics, and these are not recyclable. Because they have these chemical crosslinks, they end up being quite rigid, and when heated, instead of molding, melting, or dissolving, instead they char. And they actually comprise a huge component of plastic waste. They make up about 18% of plastics that are produced annually. That's around 65 million tons yearly, and less than 1/10 is recycled. And so you might be thinking to yourself, well, why would we use these? Traditional thermosets are incredibly difficult to degrade because of this irreversible chemical linkage that we have. It makes it impact resistant, adverse to high temperatures or hydrolysis. And so it goes into a number of different applications. But you can think, maybe we would want to keep all these properties while still instilling degradability into this material. And that's where our approach comes in. What we propose is the use of these cleavable comonomer additives. You can think of it as a small dusting of a cleavable moiety that goes into the backbone of our material. And what this allows us to do is it allows us to selectively cleave this small molecule additive and degrade our material into small enough, reprocessable, solubilizable, and easily transportable fragments. And importantly, it allows us to degrade existing thermosets, which already have existing workflows and uses. Using our CCA approach, we've shown that we can have on-demand deconstruction. As you can see here, we have a thermoset puck, and under selective degradation conditions, we can dissolve it completely. We can recover these degradation fragments and reintroduce them into a new thermoset material that matches the thermomechanical properties. And then beyond that, we can also introduce composite materials where we introduce carbon fibers or glass fibers and actually regain continuous carbon fiber through our low heat, energy efficient process. And importantly, all of this is done at low cost, low overall cost, and low loadings of our CCAs. The application sphere for this is large and wide. It can go into any type of thermoset material, but we're thinking of things like tires, wind turbines, foams, automotive parts, and acrylics. But to really ground this, we want to talk about something that might be a little bit more familiar to some of us in the room today.
Hi, everybody. Thank you, Yasmeen. So as Yasmeen's saying, there are thermosets that we use in our daily lives and we might not be aware of it. And one of them is gel nail polish. So I don't know how many of you guys have gotten your nails done and applied gel nail polish, but the way it goes, you put a nail polish that is made of monomers and photoinitiator, you cure it under UV light, and then you form this thermoset. Because it's a thermoset, it is great for whoever uses it because it has really high durability, it's really resistant to scratches, it has all the characteristics of thermosets that Yasmeen mentioned, and it's also nice because once you get your nails done, you are not worried about being still wet, you can go about your day, do your chores, and it's great. Because it's great and is resistant, it also brings some challenges. Removing gel nail polish is hard. I don't know if you guys have done it. The way it goes, you soak up cotton bond and acetone, you put it on your fingertips, you wrap them with aluminum foil, wait for 15 minutes, and then you have to scrap it. It's time-consuming, it's damaging to your skin, it's not good for your nail play. So here, we could use our CCA approach to enable easier gel nail polish removal. So we have a commercially available gel nail polish. We can add small amounts of this cleavable comonomer, expose it to UV light, and now we have a resistant film, but that is degradable under a specific stimuli. So here I'm going to show a quick video. So Here, I expose both commercially available gel nail polish and the gel nail polish with an additive to this biocompatible gel nail polish removal. Here, I try to scrape off the regular gel nail polish, so as you can see, it does not come out. And when we have our additive, when you try to remove it, it easily comes out. So this strategy of CCAs can be applied to wind turbines, but can also be applied for things in our daily lives, such as gel nail polish. Oh, it's not passing, sorry.
You're good. All right. So what we really want you to walk away with today is the idea that our cleavable comonomer strategy actually enables a number of things. Importantly, it allows us to reduce material consumption and waste generation. It reduces our total materials cost. It improves our circularity. And by virtue of these CCAs that we introduce, we can imbue new functionality and tunable performance into our materials. And so we hope that we see you at our poster and we can chat a little bit more about this. But we are always in search of some business expertise. And as Letícia mentioned, we talked a little bit about wind turbines, we talked a little bit about gel nail polish, but this approach is really generalizable. So if you have a space that you think could benefit from having degradable thermosets, we'd love to hear about your ideas on where to take our tech next. Thank you.